Why did you guys decide to create a physical AI company, and what's wrong with large language models? People are saying that all you need to do is hook large language models up to the real world and we've got physical AI. So what's the deal?
Effectively, the body matters a great deal to cognition, and more than just the body, the physical environment, the actual world that we inhabit is bundled up together with what it means to be a mind, to be a thinking thing, to exist and to live and to thrive in an environment.
The lack of embodiment is really what is sort of tripping up adoption in physical AI today. We have all these solutions for like training models and simulation. We think we can connect something like an LLM to them to derive behavior. But the fact is that those systems were not trained with embodied contact with the real world.
To state it a bit provocatively in some sense, you might say that state-of-the-art AI is stuck in data space, as it were. Basically, these systems all operate within a data space. What you don't have, at least explicitly in these models, is like a representation of the world or the situation that is generating that data. Plato says, like, it's not even the sun that's creating these shadows, right? It's a flame that's casting these shadows on a wall. So we're only interacting with shadows, we're not interacting with the real stuff.
Even with coding, for example, some people say the reason the code isn't very good is because it's not running the code, it's not testing the code. If only we had tools, if only we could get results back, then we get this feedback loop. What is the sort of the bright difference between what you're proposing and something like that?
I would say like being grounded in the world in some sense. So like no matter how you train these state-of-the-art feed-forward, gradient descent-based architectures, at the end of the day, they are only tethered to reality through us and our expressions of preferences.
This episode of MLST is sponsored by Tufa AI Labs. It is a research lab which is headquartered in Zurich. They're moving to San Francisco as well. These guys are #1 of the ARC-V2 leaderboard. They're genuinely fascinated in building the next generation of technology, the next innovation, which will take large language models to the next stage. If that sounds like you, please get in touch with Benjamin Cruzier. Go to tufalabs.ai. We have another episode of Machine Learning Street Talk, and joining me today are two very, very special people. We have Dr. Maxwell Ramstead, who is, without doubt, one of the technical heavyweights of the active inference community. I think, Maxwell, it's not an exaggeration to say that other than Friston himself, you've probably published more papers on active inference than anyone else. Is that fair?
That's kind of you to say.
Anyway, fans of the show will know Maxwell very well. Of course, we've had him on a couple of times before, and it's great to have you here, Maxwell. And we also have Jason Fox. Now, as a bit of a background for the audience here, you guys have created a company called Noumenal, and Jason, you're the CTO of Noumenal. Can you introduce yourself to the audience?
Yeah, thanks, Tim. So I come at this from a much more traditional computer science background and just down in the weeds engineer. I've been building tech for going on 25 years across many different domains, technical and industrial. Video game engines, mixed reality. I worked in defense and robotics for a number of years, kind of mid-career. And as you know, I spent about 8 years at Microsoft doing a lot of sort of really tip of the spear, sort of like R&D type work with partners as a part of the Partner Catalyst team. And that really led to a lot of applied ML, specifically around computer vision. And there's often the case where we're having to take something like the HoloLens and apply computer vision to the many different camera systems on board that, and do something useful with it, right? Or try to. And the use cases are very interesting. Like automakers like Toyota would find use for like service and manufacturing. And what that really led to was this, for me personally, this kind of love affair with, digitizing an understanding of the real world, the physical world. And so I've spent a lot of my time focusing on technologies at that intersection. And so, and then I've known Maxwell and Jeff now for a number of years. Maxwell and I together created, I think, the industry's first active inference lab a few years ago. We're excited to be recreating that again here at Noumenal and solving some real fundamental challenges in physical AI.
And just to contextualize this, you guys were at Versus before, and of course we did some great content with Versus. And this might be interesting to the audience. Jason and I were actually at Microsoft together at the same time. So we were in this group, and I was a principal software engineer at Microsoft, and we actually worked together, I think, on some similar projects. This is in about 2017 kind of time, but it's just one of those massive coincidences that we're here together. But anyway, this raises so many questions that I think we'll foreshadow now and we'll get to later. The obvious one being, why did you guys decide to create a physical AI company, and what's wrong with large language models? People are saying that all you need to do is hook large language models up to the real world and we've got physical AI. So what's the deal? But I think in order to get there, we need to go on a bit of an intellectual journey. So we'll just leave those questions hanging for now. Now, Maxwell, when I discovered Carl Friston, it was an intellectual awakening for me. The amazing thing about this podcast is we just, through curiosity more than anything else, we get to speak with some of the most brilliant people in the world, and for some reason they say yes when we invite them. So it's a win-win situation, more so for me than for them perhaps. But Professor Friston is an absolutely incredible character, and I want to get to this kind of embodiment and externalism thing, because that was what really opened up my mind. We used to think about AI as being something which happens entirely inside of the brain, almost like we could just write a computer algorithm and it would capture all of the machinations of cognizing, of being an intelligent being. Can you introduce this whole idea to us?
So I think the ultimate idea behind all this kind of physical AI, embodied cognition, is that effectively the body matters a great deal to cognition, and more than just the body, the physical environment, the actual world that we inhabit is, bundled up together with what it means to be a mind, to be a thinking thing, to exist and to live and to thrive in an environment. You might think of the embodied intelligence thesis spelled broadly as, effectively this idea that the mind, in some sense, encodes or reflects or is constrained by or depends on the specific material embodiment of the system and the very specific layout, the situation that the system is trying to adapt to. So you were referring to externalism versus internalism. This is a longstanding debate in cognitive science and in philosophy. Basically, what counts as cognition? Is cognition just something that happens in the head that involves the brain, or is it something that is world-involving? And I think basically since the late 80s and early 90s, what we have seen in cognitive science, certainly in neuroscience and philosophy and related areas, is an increasing recognition of the importance of external factors. Well, factors that were once considered external to cognition that are actually constitutive of it, right? So having a body is not, just an accident or optional to cognitive systems. All things that we consider intelligent do so through their embodied behavior in a world, right? This is relevant to AI and industry more generally because, the frontier right now is applying AI systems in the real world, right? And there's reason to believe that, if we want to do this appropriately and safely and at scale, we should draw on, the way that cognition works in the real world, the way that natural intelligence works in the world that we live in, right? And so, studying embodiment and what it brings to the table is going to be crucial. And I think one of the things that is really important and follows from this embodied mind thesis is that what's required to act appropriately in a world is to have a world model, right? So a mind is a model of a specific world, right? And of a specific body that acts in that world. And I think those are the big elements at least conceptually that allow us to frame this discussion. And maybe Jason can talk a little bit about the implications of this for like the field of physical AI, which is robotics, drones, and all of these systems that act in the real world.
Yeah, I think the key takeaway from that description, Maxwell, is that, and your question earlier, Tim, around LLMs, is that the lack of embodiment is really what is sort of tripping up adoption in physical AI today, right? It's we have all these solutions for like training models and simulation. We think we can connect something like an LLM to them to drive behavior, but the fact is that those systems were not trained with embodied contact with the real world. They have no concept of the physics, the interactions that are required to understand, how to manipulate things, and how to carve out space, understand space, move about space. That's one of the fundamental missing pieces, right? And so, I think the last conversation I think you had with Jeff, he got really deep into sort of like how language is a really poor representation of the world, right? The actual world and the way that we're experiencing it. And I think Maxwell and I wholeheartedly agree with that statement, right? It's not a simple matter of connecting something that works wholly in a digital kind of vat online or on my computer to just something like a robotic system and expecting it to work. So I do think that embodiment is a fundamental key aspect to this.
I mean, to state it a bit provocatively in some sense, you might say that state-of-the-art AI is stuck in data space, as it were. So,
Yeah.
state-of-the-art AI works by, modeling this, these vast amounts of like multi-dimensional, multimodal data. And I mean, effectively extracting correlational information from those data sets. And yeah, I mean, consider, next token prediction for like language generation or pattern completion in image generating systems. Basically these systems all operate within a data space, right? You feed data into them, and what they generate effectively is data. What you don't have what you don't have at least explicitly in these models is like a representation of the world or the situation that is generating that data. So, I mean, in some sense, you might say that state-of-the-art AI is stuck in Plato's cave. So, I mean, I'm sure most of the viewers of MLST are familiar with Plato's cave, the allegory.
Please introduce it
So,
quickly.
I mean, Plato was I mean, appropriately enough, we call his position Platonism. Basically, Plato believed that what was really real were these like universal invariant forms. So like, the form of triangle, the form of, a human, like these essences effectively. And these were like, trans-temporal. They existed outside of space and time. They didn't have a beginning, a middle, and an end. And then the things that we encountered in the world of experience were, in some sense, just mere images or copies of the actual transcendent forms that the Plato thought really existed. So Plato's cave is this allegory where he says, imagine some prisoners chained to the side of a cave, and all they can see ever is the shadows that are projected by things, as they walk by like a flame, right? So and so you see like this indirectness. Plato says like it's not even the sun that's creating these shadows, right? It's a flame that's casting these shadows on a wall. So what Plato says is like this is our epistemic situation most of the time, right? We're only interacting with shadows. We're not interacting with the real stuff. So I mean, I'm not a Platonist myself. I'm borrowing that metaphor to say, well, basically, what the LLMs and the image generators are doing is very similar to what the slaves that Plato was describing are doing. In that these systems are not really interacting with the process that's generating the data. So they're at one remove from, the actual world in some sense. I mean, that gets even more problematic when you bring language into the mix, right? Because what is language? Well, language is a representation of a representation. It's a compression of a compression, right? So I have a perceptual experience. I generate these, a model to basically explain, what is going on here. I have an understanding of the data, if you want to put it that way. And then language is a way to represent my understanding and communicate it to you. So we're now at least 2 degrees removed from the world that's actually generating experience. I mean, there are conceptual and technical reasons why we wouldn't want robots acting in the world to be stuck in Plato's cave. I mean, obviously, we would want, systems acting in the world to have some kind of direct access to the world that they're interacting with, as opposed to this indirect kind of access. There's also reason to think that, and Silver and Sutton published a great paper recently. I think it's called Welcome to the Era of Experience, where they basically say, well, we've exhausted all of the static data sets that exist currently, right? Like there is no more data that's publicly available to train these systems. So where to go from now? Well, the only other place to go is to let these systems generate the data that they want to model as they explore the world, right? So, but this pivot to agent-generated data has, as a consequence, if these systems are going to be generating data themselves, then they need to be embodied in a specific way, right? They need to be situated in a specific environment and then apt to generate the kinds of data that we find interesting and that we can continue to use to train these models. So I think all of these things are like crucially interconnected. Like there are technical limitations that are pushing us to this kind of embodied turn in AI, on the one hand, but there are also conceptual reasons to think that this is the only way to do it right.
Can I add a comment here?
Of course.
So I think that so you mentioned language as a compression, and I wholeheartedly agree. I think it's the wrong kind of compression for physics, the physical world, right? So I think that while we might walk around and sort of perceive and understand the physical world in sort of a compression-based way, like otherwise I don't think we would work, we wouldn't function, right? We wouldn't be able to take in and process everything. I think it's a different form of compression, right? And so then we find ways of relating whatever that representation is inside of our minds to other people in a communal aspect so that we can collaborate, coexist, as a society, which is what language is developed from, right? So that's one thought I had. Maxwell, I know you probably have a much more in-depth commentary on it, but.
So I think the embodiment thing is important because, I mean, you might say that mind is intrinsically related to, adaptive, intelligent behavior in a situation, right? So, I mean, it's not just that embodiment adds something to intelligence. It's that embodiment is in some sense the vehicle, through which we see intelligence as manifest in the world around us. And chatbots do have an embodiment. It's a weird kind of co-embodiment that we share with them in some sense, right? Like, you might argue that like where the grounding of the system comes from is embodiment, right? Like ultimately all of these symbols have to, like if the symbols that are being shuffled around by an AI system, or presumably the computations that are realized by my brain, if they mean anything, it's by virtue of being embedded and embodied within specific systems. That's where the meaning of all these tokens or symbols or whatever come from at the end of the day. It's not just that like embodiment is like a side thing, it's constitutive of what it means to cognize. I mean, like I was saying, chatbots have a weird kind of embodiment. I always kind of feel like we project we project the powers of cognition onto chatbots for the most part, right? Like what the LLM is doing is just completing, a token pattern at the end of the day. The fact that it is semantically relevant, that comes from human feedback. Like currently the systems that we're building make sense because we have outsourced the actual difficult labor of making sense to humans, right, who at the end of the day are like literally coders, right, who are like coders, I mean raters, right, people who like will take outputs of an LLM model and then rate it according to its conformance or discordance with like what we think is a good output. So the magic, what makes these systems look intelligent is that we have in effect projected our intelligence into them, and it's that. So that is I think also relevant to this question of embodiment. Like these systems make sense because there's a part of the system somewhere, right, the human users, that actually are in contact with the world and can tell you like, no, this does match up or not to what we experience in reality. Yeah. So I think it's really, really, really critical to recognize the if we're going to do artificial intelligence, we have to take the intelligence bit of AI seriously, and all intelligence is always embodied and situated in a specific context.
Yeah, that makes a lot of sense. I mean, I think one way of explaining this is it's not the destination, it's how you got there. So in the real world, there are these dynamics at multiple scales, and there's a provenance to all of these just almost unimaginable number of interactions through time. And causality is important here because there's a causal graph or a light cone that you can trace back through all of these interactions that have happened previously. I want to give an example of a large language model. I read this amazing paper by Kenneth Stanley the other day, and it was called the fractured representation hypothesis. So he basically trained a simple neural network to generate images of apples and skulls. And when you look at the representation map, it's very chaotic and fractured. So if you do parameter sweeps on it, the image that's generated just looks distorted and horrible. And he had another version which was trained by humans where the topology was learned over time. And there was something about capturing the provenance of information. So at university you are taught knowledge at the most abstract level, yet the kids don't really get it. It's only after a lifetime of doing and interacting and cognizing that you actually learn these kind of primitives of cognition, this world modeling that you're talking about. So ChatGPT will give you an answer to something, whereas when you really understand something, you have a kind of computational graph in your mind, which is actually a very low level understanding of how the world works. And these things, they're not Platonistic. These little kind of cognitive components, they represent regularities in the world, regularities that we've just acquired. And when you understand things at this deeper level, it allows you to be creative, right? So now your intuition is more likely to be correct. You can now riff on things and compose things and modify things because you understand it at a much deeper level. But how do we acquire these kind of little mini models of how the world works?
Well, I mean, you were saying it's through experience, and I think ultimately what happens is that we our cognitive systems are equipped such that we extract the objects that cause our sensations from the sensory data that we're generating constantly, in such a way that these objects and object types are represented to be composable. So this is how we engineer systems, right? Like this is maybe a slightly reductionist take, but I think we effectively extract objects from our experience, and when we understand objects, we understand them again, and this comes back to embodiment in terms of the possible interactions that we can have with those objects. and this, by the way, dovetails with literature on ecological psychology, right? What we extract through interaction are object types, right, that are represented in terms of like possible interactions with us and with other objects. So the representational format that we use as humans is inherently compositional. So I mean, I think that kind of gets to what you were asking, right? So like we learn object-based, object-centered representations of the world that are structured interactionally such that they can be composed. And this is where the amazing abilities of imagination and counterfactual thinking of humans come to fore.
Yeah. There is a constructive way of thinking about this, right? Which is that, the Platonistic thing is that we can decompose into this beautiful set of primitives how the world works. And anything you see is just compositions of those things. Therefore, why do you need to be embedded in the work? Because you can already just do the composition. But there's something more than that. Certainly with language, for example, it has this incredible diversity and complexity, and it just goes on forever. And certainly, even though we know many, intuitive physics, and we know a lot of deep knowledge about how the world works, we're still discovering things, and we can go in so many different directions because knowledge is perspectival and it is constructive in this way. But there are regularities everywhere. You see the same things occurring in evolution in different parts of the phylogenetic tree. You see different types of things emerging in different places, and this gets to this idea of a real pattern. And Maxwell, please tell me your lovely definition you gave me the other day of what is real. But why do we see these kind of like reoccurring motifs all over the place?
Well, I mean, I think there are there's a set of deep questions that just underwrite what you just asked, right? So like, what does it mean for something to be real? I think is like a vexed question, but it's sort of right there in what you're asking. I mean, when we were discussing a few days ago, I offered up a definition of the real, which I draw from philosophers and philosophers like Merleau-Ponty and the Lacanian psychoanalytic approach, which is something like, well, the real is when you bump into something, right? The real is when what you experience resists you in some way, I think. So that's one possible definition. I think it's a very phenomenological definition. It dovetails nicely with this whole active inference, predictive coding approach, because it kind of suggests that, well, when you're interacting with something real, it's going to frustrate your expectations about it at some level, and then you will learn from that error signal. A slightly different version of not just slightly, another take on what counts as real is what you were just describing, Tim, this whole real patterns approach by Daniel Dennett. Dennett is essentially saying, things that are real are, effectively emergent patterns. So things that arise in some way and gain enough stability so that they can be recognized and perhaps even act as like a medium for further patterns to be developed. And I think that is a very conceptually satisfying way of talking about like what is real and what counts as a thing ultimately.
Yeah, I mean, because Dennett said that a real pattern is any regularity that lets you compress data and still predict what comes next. And if dropping the pattern hurts prediction, then it earns its ontological keep. So there are many examples like in the game of life where we see these emergent macroscopic phenomena, or language is a great example. And it's too complicated for us to imagine. We were talking about this causal graph, this unimaginable amount of low-level interactions that compounded together produced this macroscopic phenomenon. It's beyond our cognitive horizon to even think about that. So we see this macroscopic phenomena and we call that a form of emergence. But this real thing, you said it pushes back on you, right? Which is interesting. So there certainly seems to be a relationship between language some people think of language as being an organism in of itself, a kind of agent which itself pushes back. But this gets us into this really sticky argument about the extent to which you could have a pressure coming back down. Could an emergent phenomenon actually have causal power? And I should say as well, by the way, that there's this wonderful guy called Mark Bedell. And in 1997, he had a paper called Weak Emergence. And he said, emergent phenomena are somehow constituted by and generated from an underlying process. And he said they are somehow autonomous from underlying processes. And this is really interesting, because how can they be autonomous if they're caused by the underlying process? And agency is a bit like this, like one of the definitions of agency is autonomy, which means it's causally disconnected, even though apparently it's not causally disconnected. And you get into these weird metaphysical discussions, because if it's not reductionist, then you seem to be getting something from nothing, right? So how do you wrestle with these ideas?
So, this distinction between weak and strong emergence, I think, hinges on whether you want emergent things to have causal powers or not. So, weak emergence, at least in my reading of it from Bidau and others, is, effectively epiphenomenal. Like what Bidau is telling us is that, some emergent macro level property, some property at the macro level emerges from dynamics at a lower level, if they can be predicted to an extent, but that you need simulation effectively to like cash out the relationship between levels. And in the paper that you're referring to, he makes the point that like this is not for him like just an epistemic thing, that this is a robust metaphysical thing. This is not just a way of talking about a pattern for Bidau. Like there's something new in some sense that emerges, but then at least in that paper, he does not want to say that these emergent properties can have kind of downward causal effects on the medium from which it emerged originally. I, as someone who worked in multidisciplinary domains like transcultural psychiatry, I kind of have some issue with that. So I was talking to one of my PhD supervisors at McGill. I worked under Carl Friston at UCL and Lawrence Kiermaier at McGill. And Lawrence is a transcultural psychiatrist, a cultural psychiatrist, and he's interested in like are they causal? The interactions between all these different levels, and as a philosopher who is interested in physics and mathematics and this kind of thing, I like nice sanitized accounts of emergence and how those things work. I'm very influenced by accounts, for example, Max Kistler's or Alicia Herrero's, who ultimately suggest that like what links levels of emergence together are constraints, not causes. What Kistler's argument, and I think this dovetails with some of the new work by Herrero, what they argue is, there are effectively two different kinds of relationships that can hold between levels of emergence or levels of organization. There's composition, which is just straight up, I am a proper part of you, right? So, the way that like droplets make up clouds, for example, and then constraint, right? So the way that, for example, like the architecture of a circuit board will constrain the flow of electrons. And those are the only two like metaphysically allowable forms of interaction between levels. The nice thing about this is that you can talk about forms of determinism that don't just collapse into like efficient causality, right? Aristotle spoke of like four different kinds of cause, and three out of those four were rejected during the development of modern science during the Enlightenment and all of that stuff. Basically, they're material, final, efficient, and formal. were the four kinds of causes. So basically what the following Descartes and all of the kind of empirical turn during the Enlightenment, all of the non efficient forms of causality were kind of banished into like the domain of like bad old scholastic philosophy, and the only kind of causation that was allowed to remain in circulation in scientific discourse was this notion of efficient causality. So like think billiard balls. For Aristotle, like efficient causation is like when the sculptor sculpts the clay into the form. It's the actual efficient process, if you want to think about it that way, or mechanism through which things affect other things materially. In the Enlightenment period, we're talking about like billiard balls colliding into each other. So basically, the kinds of force transmission, energy transmission, that became the only like viable way of talking about causality. But of course, there are like several different ways of influencing things influencing other things that don't follow this kind of pattern. I mean, so Huarero talks about constraints as things that raise or lower the energy barrier, right? The amount of energy required for there to be a specific kind of interaction. So that's cool because it allows us to talk in a very, I think, sensible way about forms of determinism that are not mere energy transfer, and these are important, right? So they're important in the context of embodiment, and in the context of the way that different levels of self-organization interface. So for example, like to take an example close to home that we all care about in neuroscience, the whole architecture of the brain, like the network structure of the brain, certainly does have some kind of deterministic influence on the constituent modules and so on. But it's not just, efficient causation, right? Like that wouldn't make much sense. But there is a deterministic influence there. And the way that networks influence individual components of the network is through this kind of constraint. And, Huarero has a nice philosophical definition in her new book. Like I was saying, constraints are things that lower or raise the energetic barrier for there to be some kind of interaction. But for Kistler, constraints are more understood in the mathematical sense of like, give me a system of differential equations. Well, each of those equations imposes a new set of constraints on the system. The certain variables have to stay within certain ranges. I was saying all of that because the way that levels are, I submit for discussion at least, the way that levels I think are connected are through composition and constraint. And that's a nice, I think, philosophically sensible way of thinking about things. An even more vexed question, which is, what is a thing exactly, right? We've been working a lot on object detection and the way that it's treated in machine learning and in the active inference literature. And like I'm a pluralist about notions of objecthood, right? I think there are several different logically valid notions of object that what we might mean by an object. I think the least constrained version, which is also the least useful, I think, is the set theoretic one, right? Which is basically like just a thing is a set is a collection of other sets, and you get this kind of a nice recursive notion, a nice recursive definition, but the problem is that that's too unconstrained, right? So the set comprised of like my haircut, the planet Jupiter, your baseball cap, and Jason's dog. That's a logical object, right? But there's no coherence to that object. Like I think when we talk about things, we have the impression that like things should hang together in a special way, right? Like if you poke a thing, then it should react to that poke in a way that's characteristic of that thing, right? Like that's usually what we think of. So in a lot of machine learning work, objects are defined. Object recognition works in machine learning, but the objects are defined in data space or feature space, right? An object might be like an identity, a position or orientation, and some translation rules. And that's a perfectly, valid definition of object. In Dennett's terms, it would be a real pattern, right, that appears in, a channel of visual information. That's a perfectly, consistent definition of object. That's the kind of thing also that will appear in language, right? Like I think, concepts are loose collections in this kind of way, but that's not sufficient as a notion of object to interact with things in the real world. Like there are additional constraints that pertain to the kinds of things that we interact with on a daily basis, like physical real world objects are not just like an identity, an orientate, or a pose, and some translation features. Like there's some additional structure there. And Tim, we've known each other for a while. You probably know where I'm going with this. But one of the things I like about the free energy principle in active inference is that they give you a nice, robust notion of object or object type that inserts itself very naturally in this kind of context. So what's missing from the data-based notion of object is like these additional physical properties that physical objects have. And under the free energy principle, this is basically the existence of a boundary. So just for the benefit of our listeners who may not be familiar with the free energy principle as developed by Carl Friston, you can think of the free energy principle as, and this is heuristically, you can think of the free energy principle as an extension of the second law of thermodynamics, extending it from closed systems to open systems that have boundaries. Think of a closed system, right? Like a volume of gas, just to be really simple. What happens in a closed system is the gradients are all consumed, and the system ends up arriving at thermodynamic equilibrium. So you might think like there's say a temperature or a chemical gradient in the cloud of gas, and through diffusion dynamics, right, what the second law tells us is that, well, the system will just tend to be uniform. The second law basically is like the law of my can of soda pop going flat, right? Like, it's uniformity is what is achieved at the end. So what the free energy principle is, at the end of the day, it's the same idea, but like physics in the presence of boundaries. So, reimagine that same system, but now there's a boundary separating, the two chambers of gas. In that context, just by construction, you said there's a boundary, so you're not going to get this strong mixing, right? The gradients are not going to be able to just, be consumed in the usual way. What you get instead is the next best thing, which is this kind of generalized synchrony, this informational coupling. It's like, well, I can't mix into you, right? So the best thing that the next best thing that I can do is become like you statistically. So that's what the free energy principle is like at a very high level. And what the key features of objecthood from that definition are like objects have boundaries, objects interact with other objects at their boundary, and therefore the statistics of the boundary allow you to define different object types. And that is precisely, I think, the kind of thing that's missing in contemporary machine learning. So, again, there's nothing wrong with language, and there's nothing wrong with existing in data space. Like it's a good thing for us that language is unconstrained by physical reality. That's what enables us to use language to imagine, counterfactual situations, and to imagine things like unicorns, right? Like, or whatever, right? To imagine things that are impossible. Like that's very useful, right? In many contexts. But, when you want to act in the world, you want to be constrained by the physics of the situation that you're trying to control.
Yeah, that's really beautiful. I think that's actually one of the best explanations I've ever heard of the free energy principle.
Thank you.
So,
it's only taken me 15 years to
Well, no, this is what we were saying earlier, that it actually takes decades of wrestling and thinking about things to understand it at this level, because you have these kind of like low level abstract functions of understanding, and you can use that to re-represent and recast and construct and create your understanding of different situations. But that really evoked an image to me. I'm almost imagine you had a computer game environment, and thermodynamics is like just a completely open space where all of the little bits can just intermingle, and it just necessarily kind of just converges to this equilibrium where energy goes down. And now, like, imagine it's almost like a Quake 3 or a Doom type level where you have all of these walls and boundaries all over the place. And if I understand correctly, the free energy principle doesn't really help you figure out what the boundaries are. It's assuming that if the boundaries are there, what happens.
Yeah, that's correct.
So we still have the fundamental problem of, like, because this is presumably one of the most important problems in artificial intelligence, is this miraculous ability that we have just to make sense of a scene, to make sense of where we are. And it comes back to the emergence discussion as well, because I think these real patterns that we use to think, they're actually an artifact of the kinds of constraints between the layers that you're talking about. So it's not like they're completely like constructed from nothing. There is a path from the world that we live in, and these constraints and these boundaries, and these actually inform the kinds of models that
absolutely.
we do.
I mean, so Juarero has in her book, Context Changes Everything. It's very interesting book, and somewhat oversimplifying her argument. She says, well, there are different types of constraints that are related to coherence in different ways, and one distinction that she makes is between limiting constraints and enabling constraints. So she says most of the constraints that we consider in physics are limiting, right? So literally, like, the constraint exists because it limits your ability to follow a certain trajectory or to access a certain region of your phase space. So a limiting constraint is like what circuits do in a processor, right? Like, so having different wires are canalizing electron flow in one direction as opposed to another, and this is what, like, gaps and all of this kind of thing in your architecture allow. You're literally preventing energy from moving in a certain direction. Again, and this is consistent with her definition, right? By heightening or lowering the energetic barrier that's necessary for a specific kind of interaction. In biology, Juarero points out, constraints typically have not a limiting connotation to them, but an enabling connotation to them. So constraints are such that they enable the system to access regions of state space that they would not, on their own under ordinary circumstances. So what she calls enabling constraints are effectively constraints that allow a new kind of stability or structure to emerge, which can then itself be, subject to selection and, become another kind of, if you want to think about it like that, a medium for, new constraints to be added on top of. So I really like this because I think it allows you to talk about, the things that Mark Beddow thought were kind of like, philosophically or metaphysically suspect, but in a very elegant way. Like, none of this is spooky. It's no more spooky to talk about, constraints and their effects on, the deterministic flow of a system than it is to talk about the way that wires, canalize the flow of electrons. Like, that seems perfectly sensible on the face of it. It's not spooky. And, I think all of these kind of multi-scale effects can be made sense of and can be explained sensibly by appealing to this same kind of explanatory strategy. The question of detecting objects is a rather vexed one. I mean, but we don't have to go into that.
I think a technical comment on that. So, Maxwell, earlier you mentioned, systems today learn in data space, which is almost entirely true. I think tying that back to the importance of embodiment and experience is really important here, and why these systems don't sort of carve things out in objects the same way that we do, right? And so we're able to interact and find the boundaries through a very natural kind of interaction with the world around us. And then that teaches us how to then identify new types of boundaries when we come across them, right? And I think that gets back to this really object-centered way of thinking about the world that's missing from machine learning today. There's approximations that the field is introducing through like physics simulation. It's a very popular technique for training, particularly reinforcement learning models for robotics today, which is I'm going to like handcraft sort of a physics scene, and I'm going to add some objects to it, and then I'm going to run my simulation, thousands or millions of times over, and expect a model to come out. And so there is this notion and this need and desire to introduce those types of interactions with like physical objects into the learning process that I think it's becoming more apparent and more important as we try to shift AI out of digital space into physical space.
Yeah, I'm trying to understand this because in the real world, the boundaries are just there, and the intelligence just is the world. It's just physics, right? So it just manifests itself in the way that you were just describing, Maxwell. But if we want to build artificial intelligence, then you get this kind of partial observability where you're a thing and you might not know where all the other boundaries are. And what you're describing here is a form of intelligence where you're modeling the interaction dynamics. So we're saying at some level of resolution, we can model almost affordances, I think is the technical term. So there's a thing over here, and this is the interface, and I can do these things with that thing. And maybe part of this process is I actually need to figure out what that thing is and what I can do with it.
Absolutely.
That's kind of exploration and exploitation, right? And that's why, systems like active inference, I think, lend themselves very well to that style of learning through interaction.
Yes. So could you sketch out how that works? So because there's a bit of a blank slate problem as well. Let's imagine that we build, because Maxwell, we spoke about this the other day about whether you're a functionalist or not, because certainly people like John Searle, they made the argument that you, as well as these algorithms that we have, you actually need this causal embeddedness. You need brains, you need machines that actually operate in the real world. And I certainly spoke with Yosha Bak, quite recently, and his view was very much that you have these kind of software agents, and currently they're being simulated by our brains, but they could be, ran in silico. So there is a bit of a lingering question for me there, whether you actually think that such an intelligence must be embodied in the real world, or if we could model it differently, maybe we wouldn't need to. But let's just be practical for a minute.
I may be misunderstanding Yosha's argument, but I kind of see him as an arc Platonist, in the sense that like what he thinks is really real are like these functions, by which he means mathematical functions, right? Which are like implemented and multiply realized by agents like us in the physical world. So he's definitely a functionalist. I don't know if I adopt the same perspective. So I mean, just taking a few steps back. I think it might be useful to, where do the primitives come from is a question that you asked earlier. So, where do like the atomic elements of thought come from at the end of the day? So I think a useful question to consider in that intellectual context is, well, why do we label things at all? Like, why do we use labels to designate things? Well, a good label improves my predictive grip on the world, right? And provides a simple, like, compressed explanation of the data that I'm trying to explain. So, why do we call, hydrogen atoms, or helium atoms? Well, it's because, hydrogen atoms have specific properties that mean that they behave in certain stereotyped ways, And by labeling a collection, like literally, like by labeling this zoo of subatomic particles that hangs together as a hydrogen atom, then I'm able to, I have some kind of explanatory or predictive grip on the situation. It literally lowers the entropy of my observations. It lowers the surprise that I have when observing them, but that I have labeled them in a certain way, right? So I mean, presumably this is what the brain is doing, right? Like there's the brain has access to like these dynamic data sets that it's generating continuously through this kind of sensory palpation of the world, and from at least from an active inference point of view, what's going on is essentially hypothesis testing or label testing, right? So on the assumption that like what I'm encountering here is an object of a specific type, then I should expect this or that data to be generated, and then well, oops, that wasn't a cat. That was a small dog, right? And then my label was inappropriate. My hypothesis was wrong. So I generated some error, and then I changed my hypothesis. I try a new label. It's more appropriate. I get more predictive power. So presumably this is sort of what's going on. Like the brain is trying to create a compressed representation or explanation of the data sources that it is privy to and that it's generating through embodied intelligent action in the world. So yeah, I mean, and this is, I think, again, this echoes the embodied intelligence thesis. There is no such thing as general intelligence, I want to say. Like, and I know that's perhaps like a provocation, but like I think all intelligence is situationally specific for precisely these reasons, right? Like, so you're grounded in a specific data set that's being generated by a specific kind of exploratory behavior, right? And I don't mean exploratory in the sense of like exploitation versus exploration. I mean like this kind of sensory palpation of the world that we constantly, engage in. And, the things that populate our ontology are, equivalent to the set of labels that we deploy to make to make sense of our sensory data, by which I mean like to compress it and to make subsequent sensory data less surprising.
Yeah, that makes sense. I mean, the thing that springs to my mind, though, is you're proposing a different form of artificial intelligence than OpenAI. There's a big narrative at the moment in the Valley that, people are talking about physical AI. They're saying that we should put large language models or similar into the brains of robots and have them interact with the world so that they can do something akin to what you're talking about. They can, even with coding, for example, some people say the reason the code isn't very good is because it's not running the code, it's not testing the code. If only we had tools, if only we could get results back, then we get this feedback loop. What is the sort of the bright difference between what you're proposing and something like that?
I would say like being grounded in the world in some sense. So like no matter how you train these state-of-the-art feed forward, gradient descent based architectures, at the end of the day, they are only tethered to reality through us and our expressions of preferences. And that's a huge problem. And I don't see any way out of that architecture effectively. I mean, Silver and Sutton point out that like something was lost when we moved to the era of big data. Like if you think of like the first machine learning systems that were using reinforcement learning, like part of their power was that they were exploring, the problem space on their own. Sutton and Silver call this the era of simulation, where like, the very early systems like operated in these simplified sandboxes. And sure, they were limited because like they're not exploring the real world with all of its vagaries and contingencies, right? Like they're exploring these ultra sanitized, like simplified environments, but there was a kind of self-directedness that you ended up losing in the era of big data. And Silver and Sutton argue that this next era that's creeping up on us will be a return to that kind of like autonomous data generation, which is really critical, I think, to have like actually intelligent systems. And this is what I don't think current AI architectures are really able to do for like a wide variety of reasons. I mean, in particular because they're not grounded, they're not connected in the right way to reality. So just to diffuse a few possible objections, like we're not claiming that there aren't implicit representations of the world in, say a large language model. Surely there must be, right? Because they are trained on data sets that feature these objects. If they are predictively powerful and if they work correctly, then they will implicitly have a representation of the world in there. But it's not the kind of thing that you can reason on, right? Or that you can use to make plans because it's implicit, it's distributed. Somewhere in this messy, jumble of billions of parameters is like a representation of, Maxwell talking to Tim, for example, or whatever, right? Like, presumably, it's there somewhere, but it's not there in such a format that, the system could use that to guide intelligent patterns of behavior, is the contention.
Yeah. You couldn't go pluck that out of the network and then use it somewhere else.
Yeah,
right?
Jason, do you want to maybe talk about the discreteness of these things and their use in, say, game environments and this kind of thing? Because that I think is the problem Jason just pointed to at.
Yeah.
These objects are not represented in the way that you could just pluck out and then edit, or they're not discrete, recognizable.
Yeah, there's a certain rigidity to that, right? Where because I don't know how it's broken down, I can't go just carve out that representation of that particular object or that behavior and then repurpose it maybe in a new or a smaller context, for example. And so there's this lack of composability that's inherent in these systems, right? And if you think about, how we learn and how we move about the world and how some of the most, I think, efficient and effective systems in the world that even humans have produced, composition is very important to that.
Yeah.
Especially for efficiency. And when we're talking about physical systems that are untethered to power sources, they've got a self-containment to them where they have their own battery pack. Efficiency is extremely important, right? And so being able to or having to transport a data center, in a robot to kind of host these multi-billion parameter models, and quite honestly, it's kind of a non-starter in any production grade system, right? And so I think learning into sort of composable bits or modules is extremely important as we move forward here into new architectures.
Yeah, I mean, if we've learned anything from the DeepSeek moment, it's that, a mixture of experts architecture will always outperform one monolithic architecture. So even the LLM, purists, if you will, are moving away from the monolithic omni-model kind of model of AI. We're kind of taking that to its logical extreme to say, well, what you really want is collections of models that are situationally specific, right? That are very good at doing certain kinds of things, and that are attuned to specific kinds of situations. That's the way that intelligence occurs, in nature.
Yeah, it's also it's ironic that LLM fans do not think that intelligence is specialized. And it's ironic because LLMs are the most specialized possible form of intelligence. They learn these jagged, fractured representations, which are basically just memorizing, very, very specific things. It's very specialized. As you were saying, Jason, they're not robust. They don't learn things abstractly. They're not compositional. They're not iterative. They work best when humans use them in a compositional, iterative way. Certainly coding is a great example of this.
Right.
You do this generate test loop, and the human, with their understanding of the world, is identifying interesting candidates, and you're running, and you're basically doing the cognizing. You're using the language model a bit like Photoshop.
That's exactly right. That's what I was suggesting earlier. The magic comes from the user. At the end of the day, it's the user that both generates this iterative loop that you're talking about that makes the system so useful. And also, the semantic grounding comes from the agent. I'm the one who tells the system at the end of the day, like, this was a meaningless, like, monkeys on their typewriters kind of thing, or actually this was a very deep and insightful thing that was just produced. Like, all of the meaning comes from us. And we draw that meaning from our specific situation that we're embedded in, because we have an understanding of context, right, and of the world that we inhabit. And for an AI system to be safe to deploy, even it needs to have something like this situated, embedded understanding of itself and other agents within a given context.
Yeah, absolutely. And it's not to say that we aren't a bit like there's the drunken walk analogy where you do something 1,000 times and one of the guys will actually solve the maze or whatever. You use the monkeys on the keyboard, but it's a similar type of thing. But I guess where we're getting to here, though, is that it's not just what we said before. It's also things like efficiency and continual learning. I mean, yes, you can do continual learning with neural networks. It just becomes quite intractable to do so. But the other fundamental thing
and it also degenerates into noise, right? Like, I always find it very interesting that these experiments where they hook LLMs up into themselves and then feed. So what happens is it just degenerates into just noise, which isn't surprising if you understand what's going on under the hood and everything. Like, but yeah, basically, like, if there wasn't a human in the loop to add structure and input semantics, it degenerates into meaningless noise, right? So not that noise is unimportant, right? We image generation works because of diffusion and this kind of stuff. Like, it's necessary. It's a necessary part of this knowledge generation thing. But if you just do that, then it degenerates into nothingness.
Oh yeah.
So I want to add actually, I have really good interactions with LLMs. I think that they help me think through stuff, right? Whatever it may be. It might be something I'm writing up, a slide deck. It introduces me to new structures of information that I am not aware of, right? But it's still, at the end of the day, it's me taking the structure and then doing something useful with it, right? I often find that, like, I can have it spit out a document and then I've got to replace the content of the document, but I keep the structure of what it gave me, right? And so I think it's very interesting in discovering these new types of structures that maybe your system's unaware of, and just sort of kind of put that in the context of a physical system. Let's say we build systems that want to explore and then exploit. Well, that exploration phase needs to come from somewhere, right? And it could be driven by language models, right? Like introducing new ideas to the system, just like we have new ideas introduced to us through reading and other forms of communication and media, right? So.
Oh yeah, totally. I mean, to build on that, we're not haters, right? Like, we don't think that these technologies are, like, useless. To the contrary, I mean, they can be greatly empowering. But that's I think the point. Like, they should be considered as, like, tools that in the best case enable cognitive enhancement. They are absolutely inappropriate as replacements for humans, and in part because they're not grounded in anything that matters to us, right? They have no understanding of the norms that govern specific situations and so on. They don't even have an explicit representation of the objects and agents in a given situation, right? So, you wouldn't want this kind of thing to act autonomously in the world, right? They're inappropriate as the kind of foundation layer for physical AI. Something else is required, which is what we're busy cooking at Noumenal. But state-of-the-art systems are still very useful if you can allow a human in the loop. It's just, they're not going to be useful in the context where people hope to deploy physical AI, like edge devices, drones, and robotics, right?
Yeah.
Some of my favorite hallucinations from LLM systems are the kind that sort of they kind of confabulate this capability that they don't really have, like this affordance that they have, but they really don't, right? And so you can imagine what that would manifest like in a physical system. It's like, so I'm thinking, reasoning using a reasoning model, and it comes up with, I have I must have a third leg that I can use, or maybe I have wheels, but I don't. Maybe I'm a bipedal robot, right? And now I dream of or kind of hallucinate this capability that I don't have, and then I try to do something that ends up being, kind of catastrophic or dangerous in a real world setting, right?
Yeah.
So that's one of the things we need to be cautious about, I think, when tying language models directly to the control systems of these things, as such as the cases like VLAs or vision language action models.
Yeah, I do find it genuinely fascinating how they are simultaneously incredibly useful, and they give with one hand and they take with the other hand at the same time. Like if I've got
Yeah,
a
yeah,
medical problem, talking to O3 is better than talking to your doctor. Yeah, if you want to come up with an idea for a YouTube video, the worst that, or actually create anything, do any writing, the worst thing you can possibly do is talk to an LLM. Humans have
yeah.
this miraculous ability to come up with ideas, because interesting ideas are always on the long tail, right? They're never in the head of the distribution. So, but
Right.
anyway, like you guys, you're building this kind of compositional system where the models and the objects are first class, right? So, if I understand correctly, you're designing a kind of system which is going to be a little bit like the OpenAI, but instead of it being a large language model, it'll be a marketplace of models. And these models, because we were saying before, the reason why LLMs aren't autonomous, right? It's interesting that people think they are because we kind of discount the human supervision, but they're not autonomous because they don't understand the world at an abstract level, right? So you're almost going to build a marketplace of models where in specific situations, these models can be trained doing this active sense making using something akin to active inference, and then they can be published and consumed by other people. So you're almost building the next cloud of models. Is that a fair representation?
Yeah, so if you read our white paper, How to Build a Brain, that's precisely what we're describing. I mean, and the idea there is we should draw on the way that cognition actually emerged in nature. So that the way the brain evolved, we think, again, this comes back to the embodied intelligence thesis, right? Brains evolved to mirror a specific kind of situation or world. They do so by basically, labeling and extracting objects from sensory data. And, as brains became more sophisticated, the ability that's unlocked is the incremental combination of these different modules into like super systems. Human cognition is multimodal, and it because it arises from a combination, an integration of modality-specific systems, and this is what enables us to, perform in such a general way. So the idea is that artificial intelligence should emerge from this kind of network structure in much the same way that the brain's capabilities emerged historically through evolution and through learning.
Yeah. So the composition is very important. I think it's not just composition, and so there is this idea of a sort of repository for physical system behaviors or skills. I call them behavior packs as sort of a way of making it pithy, but it's not just about being able to query and find those. It's about tying them together meaningfully at the edge on the physical system, right? And so this is where active inference plays a key role, right? As that sort of integrator, maybe not necessarily at the top level, but at a level that's meaningful to the system, and being able to pull the right models or determine that it needs to pull a new model is probably a better way to put it, and when that's appropriate.
Yeah, the
To
nice
do
thing
so,
about
right?
Bayesian approaches is that you're always trying to quantify what you don't know, right? So by adopting a
Yeah.
Bayesian architecture, you can develop a system that goes, hey, actually, like I don't really know what this data pattern is. Like I've never encountered this before. So, you know, can I draw on, the systems to which I'm networked? Maybe you have a model for this kind of data pattern, and then we can make sense of this dynamically. And I mean, that's how the brain works, right? Like the brain is a collective sense-making machine where, like, a pattern gets shuffled around here, and if it doesn't get, if it's not mastered by, the brain regions that are active, more regions get recruited. And it is also like, it's the idea is to solve problems collectively in the same way that, neurons self-organize to solve problems.
And dynamically, I would say too. So like, if I'm a robotic arm and I'm, used to manipulating a certain type of object, and now I have a new object that's introduced in front of me, what do I do? Right? I have no agency really to decide to try anything different or load a new model to handle that different type of object. And so, being able to, in that case, say, phone a friend or, dial up Tank in the Matrix, right, to download a new skill, I think is going to be incredibly important for the successful deployment of physical AI into systems that, are doing real work, right, the way that we want them to.
So guys, I'm going to ask a difficult question. On the value chain and the revenue model, certainly if we look at OpenAI, first of all, they scrape up all of the data on the internet, and that's very valuable. And they have to have millions and millions of GPUs, and they're very expensive, and that's very valuable. And then there's this model that you pay them based on consumption, and they've got all the secret sauce. You're describing a model where, if anything, the people using the models are generating the value themselves, because they're actually using it, they're installing it in their robots, they're doing this active inference, and it's being trained on data. So I guess the first question is, where do you guys make the money? But isn't it a weird inversion that the people using the models are kind of generating the value into the system?
Well, it is. And Jason, you can talk to how the value is generated in a second, but I just want to draw attention to the fact that what's actually valuable is the data. So, model weights are valuable to an extent, but if we've learned anything from the DeepSeek moment, from a business perspective, and if there's anything to draw from techniques like knowledge distillation, it's that, like, being the proprietary owner of a set of weights is no longer an efficient business mode for an AI company, right? Like, if I can just hook up into your API and then, train up my own system, and just it's not going to be viable, right? And this isn't to mention that, like, all of the data that they scraped off the internet, like, how many times does the copyright symbol or the trademark symbol appear in the data set? Like, they're exposing themselves, and they have, like, these lawsuits are happening. They're exposing themselves to unbelievably like painful and expensive lawsuits. So I think, the business model that they're pursuing, it doesn't work. It won't actually generate revenue. That they are floating right now because they've received billions of dollars in investment from very well endowed funders. But as a business model, I don't think it scales. And also, even if it did, we've reached the limit of that data source, right? Like, these models are already trained on all of the publicly accessible data on the internet. There's nowhere else to go from here, which, I mean, brings us back to the Silver and Sutton argument. Like, where is the new data going to come from? Well, it can only come from the systems themselves generating data through this autonomous exploration and palpation of the world. I realize I haven't talked about, like, how this makes money. Jason, do you want to segue?
No. So, well, yeah, we get into that in a minute, but you raised a really important point, Maxwell, which is that, LLM companies has been successful largely due to them being able to scrape the whole of the internet, right? So you've got this amazing, rich, canonical data source of, like, human knowledge that they're able to, organize into a really curated and high quality data set for training. And that type of data set does not exist for the physical world. And I would argue would be impossible to collect in any meaningful way, right? And so it's got to be put together, pieced together, I think, composed together, right? Getting back to compositionality, by people, a community that want to ultimately benefit from the ecosystem, right? And so I think that's an important thing to think about here. There's NVIDIA is actually really, really good about sort of promoting this new emerging physical AI community. And in fact, sorry, just a little bit of a tangent. Jim Fan, who's one of the leads researchers over there, he has this new concept called the physical Turing test that he shared in the last few weeks here, where it's a messy like scene. It's like a living room, and it's just got trash and pizza boxes and beer bottles and everything. There was a party the night before, right? And and what I want to happen is that it gets cleaned up, and a new like candlelight dinner is set up for my partner and I for the following evening, and I cannot tell if it was done by a human or a robot. And so that's sort of like the physical Turing test, as he puts it. And I think it's a brilliant kind of challenge out into the community of what ultimately the goal is for practitioners in this space. And so circling back to kind of the community effort that's required, I think, to solve that problem and pass that physical Turing test, it's going to take people enabling that data collection out at the edge on robots, and then compiling it back into a centralized source that the whole community can take advantage of.
Yeah,
right?
and it allows people to monetize their own data sets and their own models in a way that benefits everyone as well.
Yeah.
And if there's a proprietary set of interactions or behaviors that I want to keep closed, I have that option. There's ways of monetizing that for us, right, that we don't need to get too deep into, but it's kind of enterprise versus run-of-the-mill street dev community type engagement, right?
Yeah. So first of all, you make an important point, Jason. Certainly, if you look at the enterprise LLM companies, they are mostly direct to consumer. Most corporations do not want to use them, and that's why certainly Cohere is an example. They've completely shifted their model. They only do enterprise and they only do private deployments because every single enterprise, the number one thing they say is, "I want to put a boundary around this thing. I'm not sending my data to you." Right? That's very, very important.
Yeah.
But I want to push back a little bit on what you were saying about it's like OpenAI is only training on all the data on the internet. Look at Google, for example. People think that it's powerful because of PageRank. That's not really the case at all. All of these sort of statistical knowledge is learned through interaction with the users, right? So you get all of these tail queries, and users put a query in, and then they click on a result, and then Google is learning the relevance of that from the users. And it's exactly the same with LLM companies. We're seeing this. It's quite a surreptitious, sneaky transition that people aren't completely aware of. But now, certainly, a lot of the information that OpenAI learns is through people interacting with it. That's how they build their engagement models, and increasingly it's being wired up to tools, and you're installing it on your phone. But I think the important point, though, is that there's something very magical about interactive data. So certainly Tesla, they've got lots of physical AI data, and Google has street map data and whatnot. But when you have a human in the loop, you're actually learning something, even if it's one step removed. You're learning something about how the real world works, and then you're kind of putting that in the chain of how you train your model. Would you agree with that?
I would say yes, but what that tells you is that they're aware of the limitations of their original business model, right? So why is this kind of interaction interesting from a business perspective? Well, first of all, it's new data that you're generating when the problem is that you've ran out of data to train. So your users are generating new data. That's great. And it's data that's grounded in the situation, preferences, and competence of a user. But I think people don't realize that they're the product in that kind of setting, right? So, I mean, these business models are going to float for so long as people are, unaware of the exploitation, or are willing to go along with it because they get some kind of gain out of it. Presumably, like, you get a lot from using, Google's services, so you get something out of it. But I think especially when enterprise and individuals realize that, like, really where the value is the data, and that they're just giving it away to these companies who are then making an enormous profit by kind of consolidating and codifying that data. Like I think once consumers and customers become more aware of that, you'll see less of it, and you'll see a pivot towards people trying to opt into systems that allow them to monetize and commercialize their data and the models that were fitted on their data. I mean, I think what you're seeing is basically like ignorance driven, um, yeah, because this kind of data is something that these companies will one day want to pay for, I would imagine, because you're going to run out of it.
So, yeah. So the data is very important. I think, in some way we're providing a method for collecting the data, but there's another couple stages from modeling to actual like real use in a physical system, right? And if I'm using simulation to train, it's referred to as the sim to real gap. It's like, okay, my model behaves great in simulation, but when I put it on a robot, it goes haywire, right? Because feedback, motor noise, sensor noise, things that the real world brings to the table. And so that is another part of the value chain that we're addressing in physical AI. So think of what we're building as not just sort of a cloud kind of repository, but it's ultimately kind of a Docker ecosystem with all the tools to then go from modeling to deployment in a very seamless fashion, right? With gates along the way for QA testing your model, right? In simulation, testing it, we haven't talked about this a great deal, but I think there's an opportunity to provide a sort of a physical unit test, if you will, for my models by having a menagerie of robots available to provide that service to end users, to customers. And so they get to test what the model will do on hardware before they put it on their own production hardware, right? So I think there's an opportunity for a service like that that we're looking into, we're pursuing. But ultimately, like that deployment path is really, really a tricky technical challenge today. And for a variety of reasons, obviously the model behavior reason being one of the biggest ones, but there's a lot of fragmentation in deploying the models. I thought every robot used a robotic operating system, but it turns out only about half of them do, right? And so that was a misconception that I had. And so now you've got to then deal with companies, practitioners deploying in their own sort of native frameworks and ecosystems and address that as well. Right.
Yeah.
So,
yeah. I mean, I guess this is the secret sauce of what you guys are building, right? Because there are many forms of brittleness in all the things that we just discussed. Certainly, people have different types of robots in slightly different situations. But you're describing something which is a cross between like AWS, Docker, Kaggle, and maybe GitHub.
Or Hugging Face, maybe.
Hugging Face is better than GitHub. Yeah, I think that's a good way to think about it. And you mentioned Docker. Now, Docker, for folks who don't know, it was a revolution in cloud technology because, cloud did this thing called platform as a service, and that was great, but it was actually a clever form of lock-in, so you would be locked into using Azure instead of AWS. So, this Docker thing, and then we had Kubernetes. And essentially, the key thing about Docker is it's about immutability. So you could kind of represent a portable snapshot of an application running on an operating system. And you can install this thing anywhere, and it's exactly the same version of Linux. It's exactly the same version of the application. So you get this reproducibility. It's testable and whatnot. But what you guys are doing is a little bit different to that, though, isn't it? Because you're building something which is doing active inference. It's doing continual learning. It's changing all over the time. It's changing all the time. So I don't know how you would design that. Would you have kind of like a snapshot of the model at a particular point in time, and then maybe you would do some additional kind of active inference, and then a month later you would have another snapshot? How would you get the benefit of adaptability and reproducibility at the same time?
Yeah, so I think So you're right, Docker provided a really nice, it almost solved the like, well, it runs on my computer problem.
Yeah.
Right, in deployment. But even then, once you would deploy a Docker container, you attach it to a storage system, then it becomes its own sort of instance of that container, right? And it changes over time in different ways than other instances. And so I think the analogy there is that's going to happen in any physical system, is that there's going to be nuances to both the physical system itself and the environment that it's interacting with that the active inference is going to help pick up on, right? And so in one way, it's going to be just sort of unique to that instance of a system, but then, there are ways of saving off what's learned back to a centralized data source and then incorporating that into, let's say, Rubik's Cube, robotic Docker container V2, right? So can I now I have this feedback loop of learning that's not just at the local level, but it's sort of at a meta level in the whole ecosystem.
Beautiful. Well, guys, I think we've come to time. So it's been an absolute honor having you both on the show. I really appreciate you coming on.
Always a pleasure, Tim.
Yeah, Tim, thank you so much. It is quite the honor. And so thank you for all the content that you generate.